So glad to be here. Thank you, CodeBlue, for receiving us. We are very happy to be here. So this is Joe standing next to me, and I'm Nico. We both work for Microsoft at the Security Response Center, the MSRC, and we're here today to talk about Hyper-V, its internals, and some of the vulnerabilities we've seen. So why are we doing that? You might be wondering why us, Microsoft, are talking about bugs in our own products. It may not make sense for you. Well, there are many reasons for that, but mostly we want the bugs, and we know that it's hard. It's not trivial to find bugs in Hyper-V, and that's why we thought it'd be great for us to give a presentation, a talk about how Hyper-V works and how we can find bugs. You can find bugs and report them to us. And if you do that, we'll be delighted to pay you. So look at these figures, for example. Find remote code execution bugs in the host kernel that can be triggerable from the guest, and we'll pay you $200,000. That's a huge amount of money. You don't even need to send us an exploit. But if you do, we'll pay another $50,000 more. You know, before joining Microsoft, I used to be a bounty hunter. And I do think right now that this is one of the best bug bounties on the market. So think about it. Sorry. So we know that finding bugs is hard. There are not that many resources available, not many bugs documented. And so this is what the talk is all about today. So Joe, in a minute, he's going to talk about the internals of Hyper-V, and I will come back afterwards to talk about some of the vulnerabilities that we've seen.
Thanks, Nico. Yeah, so we're going to start off just giving you guys an overview of the Hyper-V architecture, really from the perspective of a security researcher that wants to go and find guest-to-host escape vulnerabilities that qualify for our bug bounty. So when we look at Hyper-V from a really high level, you can see up at the top here we have the Hypervisor, and down below we have what we call partitions. Now in Hyper-V, the Hypervisor is a standalone binary. It doesn't run inside of the host operating system's kernel. It runs completely by itself, completely isolated from everything else on the system. So it has its own unique physical address space and virtual address space from both the virtual machines and the host operating system. Now in Hyper-V, a partition is how we describe the logical unit of isolation that the Hypervisor provides to the different operating systems that are running on the system. The Hypervisor provides this isolation in two primary ways. First, we use the extended page tables that the CPUs provide to isolate the physical memory of all of the different virtual machines from each other. So they can't interact with each other's physical memory. And the other thing that the Hypervisor does is it intercepts attempts to execute certain privileged instructions. So for example, if one of the guest virtual machines tries to execute an in or out instruction, which would let you talk to a piece of hardware over I/O ports, the Hypervisor will intercept that attempt, and it won't actually let you talk to the hardware. The Hypervisor is also responsible for a number of other things, somewhat esoteric things. So it's responsible for doing all of the virtualization specific configuration and doing things like delivering interrupts to the hardware delivering interrupts to the guest operating systems.
So my obvious choice for targeting Hyper-V would be, for example, to go after the hypercores. Do you think it would be a good idea?
So it's actually not that great of an attack surface. The Hypervisor itself really has a pretty minimal set of functionality, and it's really not a great place to start looking for bugs. So let's talk about the root partition a little bit. So the root partition, or the host operating system, is a special partition on the system. It's responsible for managing all of the actual virtual machines that run. To do that, it actually needs some special access. So on the last slide, I told you that the Hypervisor prevents all of the partitions from accessing each other's physical memory. That wasn't quite true. the root partition has access to the physical memory of all of the other partitions. It doesn't have access to the hypervisor's physical memory, though. The root partition also has access to the CPU state of all the other partitions. And the reason for this access is because the root partition needs to provide a number of services to all of these virtual machines running. And we'll talk a little bit more about that later, but it needs to provide functionality like networking and storage, things along that nature. So it ends up needing access to these other VMs' physical memory.
So you think it's better to focus on the components then?
Yeah, I think that if you want to try to find interesting bugs in Hyper-V, the root partition and all the services that run in the root partition really is the best place to start looking for bugs. And last, we have the guest partitions. These are the actual virtual machines that are running in Hyper-V. Now, these partitions really don't have access to each other's physical memory. They don't have access to the hypervisor's physical memory, the root's physical memory, or any other partition's physical memory. They don't have any way that they can directly communicate with any of the other partitions either, except for the root partition. So in Hyper-V, there really is no direct attack surface from a guest to another guest. All of the attack surface is from the guest to the hypervisor or from the guest to the root partition. Now, when we're dealing with virtualization, we end up talking about physical memory quite a bit. In Hyper-V, we use the term system physical address, or SPA, to describe the real physical address of some piece of memory. And we use the term GPA, or guest physical address, to describe the physical address that a guest sees. And this is the lie that the hypervisor tells to the guest using the extended page tables. So the hypervisor can map a guest physical address onto a system physical address. We also have something in Hyper-V that we call GPADLs, or guest physical address descriptor lists. If you're familiar with Windows kernel development at all, these are extremely similar to an MDL conceptually. It is just a structure that contains a list of guest physical addresses, and it's used to describe some guest physical memory. The other thing I'd like to briefly talk about are some of the types of components. So if you're going and reversing Hyper-V, you'll see references to some of this stuff, and I just want you guys to know what it means. So in Hyper-V, we have what's called a VDEV, or virtual device. And this is a device that is either emulated or paravirtualized, and it is hosted in user mode of the root partition. And that contrasts with a VSP, or virtualization service provider, which is a paravirtualized device that is hosted inside of kernel mode of the root partition. And last, we have what we call an integration component, or IC. And from an attacker's point of view, an integration component is effectively identical to a virtual device. It is just some component that lives inside of user mode on the root partition that guest operating systems can communicate with.
Have we seen many bugs in those ICs?
The ICs really haven't had many bugs. I think there's been like one bug that's been found in the past 10 or 15 years.
10 years, yeah.
Yeah, so they're not super awesome targets, but they're worth calling out. So if you're interested in trying to find bugs in Hyper-V, probably one of the things that you're going to be wondering is, what are the components that I could possibly attack, right? What is accessible to the guest? I mentioned earlier that the root partition is responsible for providing a number of services to all of the guest operating systems that run. And this is just kind of an overview of what kinds of services need to be offered. So for virtual machines that aren't really aware that they're virtual machines, they think that they're running on real hardware, we have a whole bunch of devices that we emulate. So we have a network card that we can emulate, we have an IDE device, hard drive, optical drive that we can emulate, floppy drive, video card, etc. So just basically any piece of hardware that an operating system expects it should be able to communicate with when it's running on bare metal, we emulate that. However, emulation is super slow, And so for certain things like networking and storage, we have paravirtualized devices, which are much higher speed devices, but they require guest participation. So the guest needs to know that it's a Hyper-V virtual machine, and it needs to know how to talk to the root partition over a much more performant communication channel. And then we have sort of a grab bag of various services and pieces of functionality that Hyper-V needs to offer to the guest virtual machines. Things like live migration, so you need to be able to migrate a virtual machine from one host to another, or the BIOS firmware that the virtual machine boots off of when you turn it on. The root partition needs to provide that firmware to the guests to boot off of. We have things like integration components. So some examples of things that integration components do are time synchronization. The host or root can tell the guests what its time is so that the guests don't need to synchronize their time with the internet. Or we can have a heartbeat service. So the host will receive a heartbeat from the guests, and if it stops receiving that heartbeat, the host will know that something went wrong with a guest. So that's the kind of things that integration services do. And then we have functionality like we have an SMB server that runs in user mode that provides file sharing to some of the Hyper-V virtual machines, specifically if they're Hyper-V container virtual machines. That brings me to my next point, which is that while we have a lot of different services and pieces of functionality that can be exposed to the guests, they're not always available. Some of this stuff depends on how the virtual machine is configured. So for example, if you're running a Generation 1 virtual machine, you'll have all of these emulated devices exposed. But if you run a Generation 2 virtual machine, you will have almost none of those devices exposed because we expect that Generation 2 virtual machines can talk to all of the paravirtualized components. Certain options here are only available to Hyper-V containers. Certain options are only available if you're using specific features, etc. So when you're doing your research, it's always important to try to figure out, for the scenario that you want to target, what devices, what components are actually available for you to attack. Now, Hyper-V really is designed with the principle of least privilege in mind. Whenever possible, we try to put new code inside of user mode processes on the host. We don't like adding new code to the kernel or to the hypervisor. It's not always possible, but that's always our intent. And so if we look at where all of these different components live, which I personally think is really interesting, you can see at the top here, we have a number of things that do live in the kernel. So networking and storage, for example, the paravirtualized networking and storage components, those are in the kernel because they need to go real fast. So they just have to be in the kernel. Then we have vPCI, which is our paravirtualized PCI bus. And this component is in the kernel because it is responsible for enabling scenarios like direct device assignment and single root I/O virtualization. These are technologies that allow you to directly attach hardware into a virtual machine. So for example, you can go and attach a network card or a graphics card directly to a virtual machine. And then the virtual machine doesn't need to go through any software layers to use that device. So vPCI is in the kernel so that it can facilitate all of that. We have the VM bus, which lives in the kernel. And we'll talk a little bit more about that in a minute, but that's our high-speed communication channel. We have what we call the kernel hypervisor interface, or WinHVR, and this is really the kernel 32 of the hypervisor world. It just contains functions that call hypercalls for you. So they're functions that are wrappers around hypercalls. Similar to how kernel 32, the DLL in Windows, contains functions that are wrappers around system calls. And last but not least, we have the VID, or Virtualization Infrastructure Driver. And you'll probably see the VID used in quite a number of places, although usually it doesn't really have direct attack surface. The VID is really the glue that brings a lot of different Hyper-V components together. So as an example, if you want to create a new virtual machine, it is ultimately the VID that will call into the hypervisor to do that. if you need to add more physical memory to a virtual machine. Ultimately, the vid will call into the hypervisor to deposit that physical memory. And the vid's responsible for a lot of other things. It's used quite frequently. So the next thing that I think is really interesting to look at are the different communication channels that Hyper-V has, because ultimately you want to be able to talk to these components, right? So how do you talk to the hypervisor? The main way that a guest can talk to the hypervisor is by making hypercalls, which are really just like system calls. They have a well-defined interface, and we actually document all of the hypercalls that a guest can make as part of the Hyper-V TLFS, which is available online. And we have a link to that at the end of this presentation in the appendix. The next, there's a number of other ways that you can kind of indirectly communicate with the hypervisor. They're not the best of attack surface, in my opinion. It's things like faults. If you have a triple fault in your virtual machine and it's about to crash, the hypervisor will intercept that triple fault and can do things. If you have an extended page table fault, the hypervisor will receive a trap and will decide what to do about that. If you execute an instruction that needs to be emulated, such as an in or out instruction, the hypervisor will receive a trap, and it will have to decide if it wants to emulate that or if it wants to forward it to the host to emulate what it wants to do. Same thing for register access. Certain like MSRs can be intercepted by the hypervisor and emulated. But there really is not a whole lot of super complicated functionality in there, and so I personally don't think that it's the best place to start looking for bugs. So how do you communicate with kernel mode components? The primary way you communicate with Hyper-V's kernel mode components is over the VM bus. And we're going to talk more about how VM bus works in just a minute. So I'm just going to leave it at that for now. The next way is through what we call extended hypercalls. An extended hypercall is just a hypercall that the hypervisor doesn't want to handle itself, and it just forwards directly to the vid to handle. There's very few of them, and they're not very complicated, but I just wanted to call it out for completeness. We also have what we call apertures, and I'm going to talk more about that on the next slide because they're really used more by user mode components. And then once again, we have intercept handling here. And when I say intercept, by the way, that is really just a trap. In Hyper-V, we just call that an intercept. So whenever the hypervisor ends up receiving a trap or some other thing from the guest, that's an intercept. And kernel mode components, specifically the vid in Hyper-V, can end up being triggered due to this intercept handling. For example, if you have an I/O port read-or-write that needs to be emulated, it first gets trapped by the hypervisor, but then the hypervisor will forward that down to the vid in kernel mode on the host. So there's a number of miscellaneous pieces of functionality like that where technically you can exercise code in the kernel by having intercepts, but it's probably not the best place to look for bugs. And finally, let's talk about how you communicate with the user mode components. And user mode has the most communication channels available to it because it's where all the emulation happens. So we have I/O port emulation. So if you do an I/O port read or write, you can end up triggering code in a virtual device that's going to emulate that. Same thing for MMIO. So various virtual devices will register MMIO ranges that they want to receive intercepts for. And if you read or write to that physical address, then you will end up triggering some code path in one of these virtual devices. We have the VM bus once again, and I promise we're going to talk about it on the next slide. We have apertures. Apertures are effectively just shared sections, okay? They allow a component to map guest physical addresses into that component's virtual address space. So for all of these virtual devices, for example, that live in the VM worker process, they can choose to map some guest physical memory directly into the VMWP virtual address space. Now, if they do that, they need to be careful because that memory is still mapped in the guest. And some of you might be familiar with double fetch attacks, but one common programming problem that you can have with shared memory is you read some data from that shared memory, and then you read it a second time, and you expect that it hasn't changed, but it could have changed because that memory is mapped inside of the guest. So you need to be very careful when you're dealing with shared memory. The last one we have here are read and write notifications. So a component can tell Hypervisor that it wants to be alerted anytime a specific physical page is read or written to. Now you might be thinking, this sounds kind of like MMIO, right? Isn't that what you just described with MMIO? There's one key difference here. Read and write notifications do not advance the instruction pointer. And what that means is that they cannot emulate the instruction that caused that read or write notification to be triggered. So you literally just get notified that a read or write happened, and you then need to disable the read-write notification and continue execution, and then that instruction will actually be allowed to execute, and the program will go on its merry way. Why is this useful? This is useful for scenarios like live migration. When you live migrate a VM, you might copy a page of data from your current machine over the network to another machine. And you will then go and you will put a write notification on that page of memory because the VM is still running on the host, right? So you'll say, I just copied this page of memory over, notify me if it changes, because if it changes, that means I need to recopy it over the wire before I can fully migrate the VM. So that's why read and write notifications exist. Okay, so let's talk about the VM bus just a little bit. VM bus is a super high-speed communication channel between the guests and the hosts, and it works using shared memory. Now, the host never actually interacts with the VM bus directly. It always interacts with the VM bus through abstraction layers. From a high level, the way that this system works is the host will make what we call a channel offer to the guest, a VM bus channel offer. And a little handshake will happen. And part of that handshake involves the guest setting aside some of its physical memory to be used as shared memory for this channel. So the guest will carve out some of its physical memory and it will tell the host, these guest physical addresses are what we're going to use for the ring buffer. The host will then map that memory into its virtual address space, and either side can then write data into that channel and send an interrupt to the other side, letting it know that there's data waiting for it. Oh, one thing I'd like to note here is that if you're interested in how either the VM bus protocol works or any of the client-side code for, or I guess I shouldn't say client-side. What I mean is the guest side of these virtual devices work. You can easily figure that out because all of the source code for VM bus and the guest side of these virtual devices and VSPs is checked into the Linux source tree. So we have links in the appendix here. You can go and check that out. There's no mystery there. So I mentioned that VM bus is never interacted with directly. It's always interacted with through abstraction layers. On the kernel mode side of things, the way that we interact with it is through KMCL, or the kernel-mode client library. This interface is really built around callbacks. So when you make a channel offer, you also register with KMCL a number of callbacks for things like, call this function whenever I receive a message from the other end. And you might be thinking, well, VM bus sounds dangerous because it uses shared memory. And so all the devices that use VM bus are at risk of double fetch attacks. However, the messages that get sent over the VM bus actually get copied into Windows kernel pool memory before they are delivered to the device that is using the VM bus. So they are copied out of shared memory into memory that's only available to the host. So there's no risk of double fetch attacks there, except for this mechanism we have called external data. So I had mentioned earlier that we have GP80Ls in Hyper-V, or guest physical address descriptor lists. And one of the things that you can do when you're sending VM bus messages over the wire is you can actually attach a GPADL to that VM bus message. And it's called external data in the structure definition. Now, in order for the host to use this external data, it needs to explicitly map that data. So nothing will just magically happen under the covers. But the host can choose to map that data, and if it does need to be very careful because that data is mapped in both the guest and the host. Now, at the end of the slide deck in the appendix, we have lots of function signatures that we documented to make it easier if you want to reverse engineer Hyper-V. But this is just a super brief example. This middle function here, that's what the callback looks like for the VM bus. And so the third parameter is the buffer parameter. So that's just a pointer to the message that you're receiving. And it's in safe memory. It's in pool memory. So KMCL is how the kernel mode components use VM bus, but what about user mode components? The most common way for user mode components to use the VM bus is through VM bus pipes. And a VM bus pipe is an interface that's set up to look exactly like named pipes on Windows. So the way that you start using a VM bus pipe is the component, the virtual device or integration component, will once again make a channel offer, but the channel offer will give it a handle to this VM bus pipe. And it then interacts with it using read file and write file, just like you would with a normal named pipe. Or you can do asynchronous I/O if you want, using I/O completion, once again, just like you would using normal named pipes on Windows. So that one's really easy to understand. Once again, at the end of the slide deck, we've documented a bunch of the ways that components will stand up VM bus named pipe channels to communicate with the guests. All right, and the last communication channel that I want to just briefly talk about are I/O ports and MMIO entry points, just to give you an idea as to how this looks in the code. So for I/O ports, you can see it's really simple here. Basically, any device that wants to use I/O ports needs to implement these two functions, a notify function that gets called when the I/O port is read or written to. And that function just tells the component, here's the I/O port address that was called. Here is the size of the access. It's 1, 2, or 4 bytes. And it'll either give you the data that's being written, or it will give you a pointer to the data that you are expected to fill in as part of the emulation. And it's pretty much the exact same story for MMIO. You're given, you have to implement these two functions, and you'll be informed the number of bytes that are being read or written, given a pointer to the buffer that either contains the data or that needs to be populated with the data. So at this point, I hope that you guys have at least a somewhat decent understanding as to what sorts of attack surface there is in Hyper-V, what sorts of services we need to provide to virtual machines, and what sorts of interfaces we commonly use to bridge that gap between the guest and the host operating system. And so now Nico wants to walk you guys through some of the cool bugs that we found in Hyper-V that lie behind these communication channels.
Thank you, Joe. That was super useful. Before we even thought about giving this talk, we were asking around us why was it so hard for researchers to find bugs in Hyper-V. And one of the most common replies that I had was, Nico, you don't seem to realize you've got access to source code, you've got access to case reports, you've got access to everything, but we don't even have access to symbols. And that's actually a very good point. So 6 months ago, we opened our symbols for Hyper-V. So not all of them, fortunately for you, but there is definitely enough there for you to start reverse engineering. I think right now there's around 40 symbols. They are really decent, and they are definitely what you need to look for bugs. Joe, I think I've seen a tweet from you last week about that. Do you want to?
Yeah, so we actually, as of about a week ago, we released the symbols for all of the Hyper-V storage components. We had accidentally not published a few of them that we meant to publish. And so actually, as of right now, symbols are released for every Hyper-V component except for the hypervisor and the hypervisor loader. But all of the attack surface in the host operating system, we've got symbols published for all that stuff.
That's great. So just keep checking out that link at the bottom of the page, because maybe one day the remaining symbols may be available. So let's talk about some bugs now. So we've selected there's 5 vulnerabilities. So why there's 5 in particular? Well, some of them were reported by externals, and that's good. That's good because here we can tell you their methodology, how these guys found bugs that we, Microsoft, didn't find before. Also, all the components here that have been affected by these vulnerabilities have public symbols. So you guys, if you want to reproduce these bugs, you can just, with the symbols, put your breakpoint and try to reproduce against the vulnerabilities. And last point, crucially, these bugs are easy to understand. We've seen incredibly complicated bugs. We've seen bugs that would take at least more than 1 hour to talk about. We just don't have time to talk about these bugs here. So just to give you a quick overview of what I'm going to talk about. So 2 bugs affecting the kernels, mostly VM bus, and other bugs affecting the I/O ports. So I'll start with 1 bug affecting VM switch. So what's VM switch? So Joe quickly talked about it in the architecture. So this is what provides a network. This is a component that provides a network connectivity to the VM. It's a huge component, so go have a look, try to reverse it. So the first bug was reported to us a while ago by somebody named Peter Alvarti, working for Tencent. And unfortunately for us, this bug had to do with a long string sent to the host. So Peter found a way to trigger a crash in the host just by sending a packet that was embedding a string without a null character. And so what was happening there is that between TH2 and RS1, the developers added a function in a function that was actually reporting errors. And so in the set network address function, if an error was detected, that function was logging the string. And it turns out that we didn't check if the string was null terminated. So if you were applying the special flags to VM switch at that moment, you would be able to crash the host. For a bug like this right now, we would pay $15,000. And that's almost what Peter got. I think he got 10 because that was 2 years ago when he reported it. Yeah, so we keep increasing our bounty also. So what Peter did, how did he find this bug? He was clever. As Joe mentioned, the Linux drivers are available, and that's exactly what he did. He fetched these drivers, he studied them, got an idea of how they worked, and then he just implemented a quick fuzzer, just something that was just sending packets to the host. And since this vulnerability was really easy to trigger, he got it within 5 minutes. Afterwards, he just built up a small POC, just consisting of lines he borrowed from the original source code, and then sent his packet with the long string to the host. And that was enough. That's what we got. It was an easy to reproduce bug, and we are very thankful that he sent that to us. So if you guys want to reproduce that vulnerability, you might not see a direct relationship between the vulnerable function in question and the VM bus. It's just because these requests are processed asynchronously. So just put a breakpoint in the vulnerable function, and at some point it will be called. So just to finish on VM switch, we we should mention that some bugs have been reported to us before by Kostya Korchitsky from Google, so that was 3 years ago, I think. These bugs are publicly documented. Proof of concept are available, so you can have a look at them. And also, Jordan Rabbit from the Offensive Security Research Team at Microsoft gave a very interesting talk at Black Hat this year about an exploit he did for VMswitch 2 years ago, I think. Check out that talk, it's very interesting. All right, so we stay in the kernel, and this time we're going to talk about VPCI. So VPCI, what is that component? So it's basically what the component that the guest is going to use when he wants to use a PCI device on the host. So for example, if you have a guest that wants to use your latest graphic card, that's probably the component that it's going to use. So in the host, you've got VPCI VSP.sys, and in that driver, you've got a big switch case. It's virtual, well, whatever that function name is. It handles 25 cases. In one of these cases had to do with create interrupt request messages. So what that cases was doing was using a stack buffer and giving it to an internal function. If you look at how this internal function is handled, you'll see that the initialization of this stack buffer is done at the very end of it. Unfortunately, what the developer didn't do at that moment was to initialize it before, in case an error or an issue or an exception was detected. And that's exactly what happened. So this bug was found by the virtualization security team at Microsoft. And they figure out that by causing an issue, an exception in that function, the stack buffer would be left uninitialized and sent back to the guest. For a bug like this, where you can leak stack memory from the kernel, from the host kernel, we would pay up to $25,000. However, we would need a POC. For this kind of issue, generating a POC is not that difficult. I do advise you to just put a breakpoint on FDO protocol communication in the guest in VPCI.sys, and just look at how the handshake is taken. And then you can just change your messages and try to fuzz it and see if that gives you any result. It's up to you. So next, we leave the kernel and we move to the worker process, but we stay with the VM bus. So I'm now going to talk about a synthetic device, sorry, which has to do with the resolution, the screen resolution. So this component is handled by VM-UI device, .dll, in the worker process. So you've got this, again, a switch case in that component, which handles just 9 cases. It's very easy to, not only this component, there's not only this particular component in this DLL, there are also others, but the reasoning is always the same. Just look at the endpoints, how the messages are processed, and try to figure out what's going on. This is, the code there is really easy to understand. So the bug in question here had to do with a particular message sent by the guest. So the guest would send a message and set a Boolean in that message to false. In which case, the host would see that Boolean and would return a message with a structure that was not fully initialized. So I found that bug like 2 years ago, just by looking at not at the sources, but at the DLL itself with IDA. And something surprised me. I only saw just a couple of fields initialized, but the size used in the allocation was much bigger. And it turns out that several fields were not initialized there. So in the end, we would leak up to almost 90 bytes of heap memory from the worker process to the host. A bug like this right now, if you report that to us, you'll get $15,000. In this case, there was also another bug present in another function. So do some research like this, and you'll double your bounty. However, you need a POC, or at least something that we can reproduce easy. So one thing that I haven't mentioned so far is that we don't necessarily need a driver. We can, you can, for example, just send us a script, a WinDebug script, something that put a breakpoint in that function and just change the message to a particular type. This vulnerability is very easy to trigger. So you just send a message to the host, to the worker process, set that Boolean to false, and then the response with the initialized data is sent straight away to the guest. That's very easy to see. We don't need a driver for that. Just a script would be enough. So next, we leave the VM bus, and we are talking a bit about the I/O ports. I think, Joe, you want to talk about that one, because you found it?
Yeah, so this one, it's actually an MMIO emulation. So one of the things that we had mentioned earlier was that these various virtual devices that implement MMIO emulation have to implement this function, notify MMIO read. And the way that this function works is that it's called when you try to read from a guest physical address that's used for MMIO, and it will be informed as to the number of bytes that the guest is trying to read, and it is expected to populate that read buffer with that many bytes. And the issue was that there were actually some emulators that we had which would, in error cases, not initialize that buffer. So you can see here this example of the battery emulator, which is used to tell a virtual machine running in a laptop how much battery that laptop has. This emulator was expecting that there would only be 4-byte reads happening to its MMIO range. And so if you tried to read anything other than 4 bytes, it would just return. So this means that if you try to do an 8-byte read, then you will read 8 bytes of uninitialized data. And actually, this bug was kind of nice because it turns out that the 8 bytes that I would read was always, well, when I tested it at least, it was always a pointer to a very specific object on the heap. So it's a pretty nice way to break ASLR if you had another memory corruption bug you were trying to exploit. And this bug, if you found that today and reported it to us, we would pay $15,000 for.
I'm glad you got it, Joe, because I missed it. So the last bug we are going to talk about is actually your favorite. It affects the emulated ID component, which is used by, as you mentioned before, the floppy disk, the CD-ROMs, the ID drive, and it's definitely our favorite. So it was reported to us by somebody who wishes to remain anonymous. So this component, what it is, so you talk to it through 8 ports. So the first 7 ones are just to set its internal state. The last one is more interesting. If you read or write data to this port, you're going to end up in that function that is read-write data port. So if you look at this function, you'll see that quickly in the beginning, the code is doing a test on the state, on the internal state. And if the internal state is set to a particular value, then it's going to use an offset to index into an internal buffer. And this is where the bug is. So the guy who found that just fuzzed quickly the IOs and managed to get a crash involving this buffer. And what's crazy here is that you could control the offset. It's a 4 bytes offset. So you could, in the end, get an arbitrary read or write primitive on 4 gigs on a heap segment. And this is super useful when you're looking to write an exploit. So I'm glad to tell you that today, up to now, that's the highest bounty that we've paid, $150,000. This bug, it's it was trivial to find. It's just a sequence of out instructions. It's trivial. I hope we don't have that many bugs remaining. Anyway, we'll see. Joe, do you want to have some final words on this?
Yeah. So thanks for having us here. We've really enjoyed being at Code Blue. We hope that this talk has been interesting for you. We hope that some of you are interested in participating in our Hyper-V bug bounty. I personally think that Hyper-V is a super interesting target to go after. It's really well designed in my opinion, and the code quality is quite high. So it's definitely not an easy target to go after, but when you do find bugs, it's very gratifying. And of course, our bug bounty pays quite a bit of money. We really want to pay bounties, so please do send us bugs and let us know if there's anything that we can do to help you guys do research on Hyper-V or other Microsoft components. And yeah, as Nico had noted, Jordan had given a talk at Black Hat earlier this year, which was also about Hyper-V and exploiting some bugs he found in the VM switch. So if you are interested in Hyper-V and you want to see more interesting Hyper-V research, you should definitely check that out. Yep, that's what we got.
So thank you. Thank you, guys.
Thank you.